Okay, we are alive. Although I don't think I have the right microphone. Oh, I don't have the microphones on yet. I haven't finished the hardware setup. Palo Alto.
Where's Uptown 200? That's what Christy Brinkley hang out there?
Is this working? Is this working?
Does everyone here have a mental picture of the Granny Juice commercial where Granny's set on Canditos? What's the bag?
What's the what?
That's better than a mental picture. I had a YouTube video
That you may have seen.
Although, no, this is not right yet.
The good, the bad, the good, the bad, and the other. The guy who was the other. And if you look up on the YouTube, what's in the bag? Question. Yeah. Right.
Okay, am I on? Yeah, okay, great. Let me just get the start screen. Okay, shall we start?
It's up to you. You have the wire.
Okay, I got the wire. Okay. All right, let's get started. Okay, for those on the internet, this is Silicon Valley Fourth Interest Group, the June meeting. And the morning session usually was called Fourth Modification Laboratory, formal. Okay, if you guys remember. But but I think we have not done much fourth modification lately. What we were doing was a CPU modification laboratory. So this one is probably the last of the CPU design sessions. Okay. Well, I think it got to be my last. Okay, so you know, last month we had a CPU design workshop, and we got 16 people participating. I think 4 people actually got the 8080 implementation working. Okay, so that was pretty good. And then I was reviewing all the historic processors, and then decide that you know, I did 8080. Probably I should do a earlier one, just to show that we can do it. Okay. And the one I picked was PDP1. The reason in picking PDP1 was that I was watching the recording, the YouTube recording of the PDP1 restoration project in the Computer History Museum. I don't remember exactly when it was probably a couple years ago. They restored one of the original PDP-11 and had a big celebration and invited all the original designer and many of the original programmers who developed various applications for the PDP-1. So that video was very inspirational because it mentioned that PDP-1 was the first machine built by DEC, and DEC actually gave that prototype to MIT. So all the people in MIT was basically latched onto this PDP-1 and doing everything they can. I think they have a sign-up sheet in front of the room, and people can sign up for maybe an hour or 2 hours, and they just rotate it. And many people get their hands on this computer and develop lots of things. And when DEC released the PDP-1, it didn't have any software to go with it. So what they had was the programs that MIT people did, and they just grab onto that and showcase their PDP-1, and it aroused lots of interest. And the interesting thing about the PDP-1, from my point of view, is that it is the first personal computer. Of course, it is the first mini computer in the process of shrinking. Okay, and it is the first personal computer in the sense that before that, the computer really doesn't have any personal characteristics. It just have the corporate characteristics. Whatever the IBM gave you, that's it. You just do whatever IBM allows you to do. But this machine, people can use it basically boot it up by switches, and then load from many input devices, and then get the program to run. So this morning I would review a little bit the PDP1 architecture. I will talk a bit more about the PDP1 instruction set, because that's where I have problems. When I try to implement PDP1, that's looking through the instructions and try to realize these instructions in my FPGA. So I would talk a bit more on this instruction set. It is also interesting. And then the FPGA implementation. And then I would elaborate on the eForth implementation, the software side of this project. I'll do some demonstration, and then we have the open floor. And this is the restored PDP-11 in the Computer History Museum. Yeah, PDP-1. Yeah, I'm sorry. And I think this guy is the guy who first do the space war or something. Yeah, the first game that's played on this CRT behind him. Yeah, so that's the PDP-1. I don't remember which one this is. Okay, it may be the original one given to MIT, or maybe a later one, but that's the original.
Go to the Computer History Museum
Yes.
today and play Space War again once or twice a month. They have that.
Yes. And so that's the you know, they have reduced the size of a computer from a room-sized setup to a refrigerator size. So that's the very significant step. And this one has, as I read, it's 2,700 transistors and 3,000 diodes as its building blocks. So that's the original one, and this is mine. Okay, actually the PC is a development system. The PDP1 can be reduced to that size, and if we can have a close up. So that's what I did in reducing that refrigerator-sized PDP1 to a single board, or one chip on a single board. Okay, as you when the ENIAC was the first electronic computer using vacuum tubes. But ENIAC is not really a computer. It is a giant calculator. Okay, so it is using decimal BCD logic to do add, subtract, and multiply and divide. And when von Neumann visited the ENIAC, he immediately saw that this is not a computer. And so he went back to Princeton and wrote a report and basically delineates what a computer should look like. And this is what the von Neumann architecture. The von Neumann architecture, basically, it has two registers, an AC and MQ. The AC is doing all the normal logic, and MQ is multiplier or quotient register. And when it is used with AC register, it does the double precision multiply and divide. So that was the central portion, central registers of the von Neumann machine. And the instruction-wise, it has 40 bits words, and the 40-bit word are divided into two. So each instruction is 20 bits. In the 20-bit instruction, there are 10 bits of code field, 10 bits of instruction, and 10 bits of address. So the original von Neumann machine can address 1K words of memory. And it has 10 bits of instruction, so it can do 1,000 different instructions, but it only designed, I think, about 20 instructions. So PDP1, just like the 701, IBM 701, adopt this architecture. And the only difference is that instead of 40-bit words, it's using 16-bit words. Essentially, it's using it reduced the 20-bit instruction into 16 bits. And among the 16 bits, there are 6 bits for instructions and 12 bits for address. So it can access 4K words of memory. It has the AC register, and it renamed the MQ register as IO register. I think the purpose of it was that besides doing the multiplication and divide, it is drafted to do the IO operations. But this is not the IO I/O functions of this register is very limited, so I'm not using it to that extent. So 16-bit instructions, it has 5-bit opcode, so it can host 32 different instructions. And there's 1 bit of indirection in that if this bit is set, the memory address is a relative, indirect address. So it fetch the address and use the content, the content as an address to fetch it's a pointer, yes. And then 12-bit of address. And this is a picture of it. So we have an AC accumulator and I/O register. And beside that, you have a P register, 12-bit P register to provide addresses to fetch the next instruction. And it also have a, I use an A register to store. If you want to fetch data from the memory, you use the content of the A register. And when an instruction is fetched, the instruction is latched into the I register, and 5-bit of it is put into the code register, and which drives all the decoding logic. And 12-bit is latched into the P register so that it either execute the next instruction from that location or fetch things out of it. So here, the ALU is basically a gigantic multiplexer, and it accepts information from the data bus, from the AC register, from the I/O register, or from the A or P register, and then do the necessary arithmetic or logic operations, and then feed the data into the AC. So, and the I/O has a similar one, but because the I/O register, is very limited, and this multiplexer is much smaller. So all this thing allows you to read one instruction and use the code field to decide what to do. And if this is a memory reference instruction, it would go out and get the data from a memory, and then do the logic. And on the rising, so the first cycle is instruction fetch cycle, and some of the instructions can be, if it doesn't need information from the memory, it can be executed in a single cycle. If it needs to access memory, you have to add one more cycle. If it is an indirect instruction, you have to add another cycle. So this is the basic design. So the PDP11, we have a 5-bit code field, so you can have 32 different instructions. And the majority of the instructions are the memory reference instruction. So it is, these instructions has 5-bit instruction code, 1-bit indirection, and 12-bit field, which specify the second argument to be fetched from memory. So it includes arithmetic instruction, logic instructions, and other general instruction which fetches and stores the registers. And then the augmented instruction. Because there's only 32 instructions, which is generally not quite enough. So they have specified several different code and use this code to do what's called the augmented instructions, which uses the 12-bit address field to specify other arguments necessary in the instruction. So you can do in one of the instruction, which would allow you to do the shift and rotate. And this is a very sophisticated design. And then another instruction allows you to do skip, to skip the next instruction based upon logic conditions. And then there are other miscellaneous operations. So the memory reference instruction, this is the almost 30 of them, and they are the outcode there, the address there, so you can do AND, OR, exclusive OR. This is call subroutine, but I think at the time subroutine call was not matured yet. So this subroutine call is not really a subroutine call as we understand it. And this LAC load into the AC register. DAC is deposit into AC register. DAP is deposit only the address part and into the memory. And this deposit only the instruction part. And DIO, it is the load deposit into IO register. I think there is one which loads into IO register, which I think I missed that. And this is the deposit 0 into memory. Add, subtract, multiply, divide. And this multiply and divide are the multiply step and divide step. And increment, this is called index, increment and skip. And skip if A is different from the memory. Skip is AC register is the same as the memory. So the mnemonics are kind of very well designed. So you can read it almost and jump. This is jump and store P register, skip and shift. So this is the basically the instruction set. But the skip, shift, these are two augmented instructions. I'll show you. Okay, so this is the ALU instruction, which basically does all the things that you normally want to do with the addition of multiply step and the divide step. Okay, this is the register. You load into AC, you deposit AC into memory, and so forth. And then this transfer, you can execute the instruction in the memory location Y, or jump to Y, jump and store the program PC, and so forth. Okay, so fairly good. And the shift and rotate, that's one of the problems that I have. It is the opcode is 64, okay, and the rest of the bits specify the way to do the shift and rotate. So one bit. Oh, I'm sorry. I think this is the skip. This is not the. This is a skip. Okay. So here there are 5 bits specify reading 5 status bits: 0, positive, negative, overflow, and and this is there's an internal flag and there's a switch, so you can skip on some internal program flags and the switches, the manual switches. Okay, so this is interesting because these 5 bits, the 5 conditions, are all ordered together. So you can have multiple logic going into the skip condition. And then remember the indirection bit. The indirection bit is used to reverse the logic. So whatever the condition which will normally cause it to skip, if this indirection bit is set, it will not skip. It will reverse the. So this is extremely powerful. But usually our minds, or at least my mind, doesn't work that way. So I can only take one condition at a time. So it is a very nicely designed system, but I think for us, fourth people, we only skip on 0. Okay, so that's the only condition we understand or we use, and all the other ones can be ignored. Okay, this is the shift and rotate instruction, and it can shift or rotate the AC register alone, the I/O register alone, or shift the AC and I/O register combined as a 36-bit big shift register. So you can all these shift right, shift left. 1 bit specify to shift or rotate. Another bit specifies shift right or left. And the next 2 bits specify whether it's AC alone, I/O alone, or AC and I/O combined. So very powerful. And it is this instruction I felt I could not implement easily, because you see here it got the 6-bit code bit, and then 3 more bits for the shift conditions, and then there are 9 bits left in the address field. And the specification reads that if any of the 9 bits are set in the address field, then you shift that many bits left or right. Okay, so you can shift in one instruction, specify shift 1 bit to 9 bits left or right. So this is extremely powerful, but it's very difficult to implement. So I decide, instead of following the exact specification, I say I just do 1 shift at a time. Okay, so that's one thing I didn't do exactly as specified. You know, this is a gigantic barrel shifter. It's a 32-bit, in general, a 32-bit barrel shifter. Okay, and to accomplish all the shifting that's required in a single cycle, the logic is enormous, and I didn't think that I could do it in the very limited time I need to have it done. So I just want to say, well, I'm writing the software as well. So if I design the shift register only shifting only 1 bit at a time, I will, if I need to shift more than 1 bit, I'll do it in software. But later, I thought that this can be implemented very not very easily, but it can be done. But I just add more cycles to it, to the instruction. If I have more bits in this 9-bit address field, I just test each and every bit and test it 9 times. And if there's any bit which is set, I do the shift. If it's not set, I just not do it. So, adding 9 more cycles to this instruction, I can use the same shifting circuit to accomplish what this instruction required. But I think this is if I have time, I probably would do it, but I probably would not do it. I just leave it alone. So the skip instruction, as you see, this is the skip instruction. The indirection bit is a no. If it's 0, you do the logic. And if it is 1, you invert the logic result. And then you can shift down positive, shift on overflow, shift on minus, shift on plus, shift on 0. And the switch is the panel switch. There are 6 switches on the panel. And the software can skip on the condition of these switches. And 6 program flags that the software can set. And then can skip on these flags. So let me see if there's anything. This is the shift and rotate instruction. So here the code is 66, and this indirection bit is to the right or left, and shift or rotate. And this selects this bit selects I/O. This bit selects AC. If both of these bits are set, then sorry about it, this should be a 0. If both of these bits are set, then it is a combined shift. And then these 9 bits here specify how many bits to shift. So it is not just a number at the end. It is each and every 9 bits telling the machine to how many bits are shifting. So if I shift, there's 9 different ways to specify shift at 1 bit. So any of these 9 bits are set would cause shifting 1 bit. But if all 9 bits are set, you shift 9 bits. Okay. This is a challenge for CPU design, for CPU designer. And then there is some miscellaneous. IoT is doing I/O, and the load accumulator with a number. So this allows you to load a literal. And if so this is 70. If the 71, if the indirection bit is set, then you actually load the negative of the literal. So it is yeah. So it's quite powerful with 18 bits. 18-bit word size, you can do a lot. Okay, in my implementation, the indirection bit is a big problem. because the indirection bit, if it is in the instruction, it specifies the contents of the address. If you go into the memory, in the memory, if this bit is set, it is another level of indirection. Indefinitely, okay? So that's, I don't know, anybody can indirection, 2 levels of indirection. Yes.
Yes, C, you can. In fact, I've seen 3 levels of indirection. Yes. Basically, what it is, we have 1 level, say, a pointer to something.
Yes.
2 levels, a pointer to a pointer.
Yes.
And 3 is obviously pointer to a pointer to a pointer.
Yeah. And the hardware, it specifies if the memory has this this bit set, then it's another level in indirection, and there's no limit to it. In the memory, So in the memory, there's no limit to the indirection. Yeah. It was horrible. It's horrible.
Depending on the contents after the address.
Yeah. Yes. In the memory, you remember? Yeah. Remember, it's a 18-bit word. Okay. So there's a 12-bit of address, and on the next bit above the address, that's the indirection bit. Okay, if this bit is set, the memory goes another level. Okay, and this is especially problematic for FORth, is that I want to implement a dictionary. Okay, and I cannot guarantee that this indirection bit in memory is always cleared or set as required by indirection. Okay, and if I have instructions in the memory, I can control it. But I have name field in the instruction. So the name field is I have 2 bytes for in each 18-bit word. I can store 2 bytes of name, and I cannot guarantee that the indirection bit is always 0. Okay. But you have to fetch the name, right? You don't have to go there. You don't want to go there, right? You just want to fetch the name. But if the name has this bit set, then you will go somewhere else. So this is a very big problem. And so in here in my design, I say I only allow indirection bit in instruction and not in memory. Okay. So this is I think it is ridiculous to allow indirection to go in indefinitely, and I think it's unreasonable to even go 1 level. Okay, so I do not allow indirection in memory, and I think I didn't talk about it in the instruction set. The instruction set have an increment instruction, increment the content of memory, and it has an increment and skip if positive. Okay, so it has these 2 instructions. I need the decrement, okay, because of the stack. So when I manipulate the stack, I have to be able to increment the stack pointer, and I have to decrement the stack pointer. So without that decrement instruction, it's going to be horrible, because you have to do the decrement in software, and it's very costly. So here, because you see there are 3 empty slots, 3 instructions, 3 empty code. So I'm using 2 of the empty code to implement a decrement and a decrement and skip if negative. Decrement and skip negative is the one that's required for looping. Okay. So in eForth, when we implement the loop, we push the count onto the return stack and decrement the count going through every loop. And when the loop count is negative, I'll leave the loop. So I add decrement memory and decrement and skip if result is negative. So this is absolutely necessary for a fourth machine. And shift and rotate, as I said, 1 bit at a time. Okay, it's much easier to do, and I don't have to worry about this gigantic barrel shift. The I/O instruction, I think at the time of PDP11, the I/O was not understood completely, or the I/O device has not been streamlined. So when the PDP11, when it has to read the tape punch, a tape reader, everything has to be designed, and tape drive, the magnetic tape drive. Every device has to be designed separately. So the I/O instruction is I just couldn't understand any of it. So I said, well, I'll just do a UART. I'll just do a GPIO, and that demonstrated the gave a general scheme on how to design a I/O device and hook it up to the PDP1. Another problem in reading the specification is that the subtraction is done in one's complement. Okay? And, so no, I just do it like two's complement. Okay, because I can do it in one's complement, but then I have to worry about it in software. So I just it's just easy to do it in one's complement or two's complement on the VHDL. Okay, so it makes no difference for me, and it's much easier on software if the subtraction and all the arithmetic operations are two's complement. It's easy. One's complement, you just add 1 to it, right? But this brain is not big enough. So these are the deviations. So I think to design a CPU to revive an old CPU, one way in thinking is that you do implementation which exactly replicate the original, so that your machine can run all the software, all the historical software developed for that machine. So that's one of the approach. But I don't have access to any of this old program. I'm not familiar with. I don't play games. Space War. What is Space War? I have no idea. So I'm not latched into the tradition software in here. So I thought I just do it my own way. What I want to do is that I want to implement FORTH on it. Okay, and because that's my debugger, or that's my benchmark, the test bench. Okay, so in designing a CPU, you need to design a test bench to verify that all the instructions are working according to specifications. But it's more difficult to write a test bench than the CPU itself. Okay, it's much more work. My approach is that I would write a FORTH for it. And if the FORTH works, wherever FORTH touches is verified, okay? And of course, wherever FORTH does not touch, it may not work. But once you have FORTH working, it is easy to fix anything that you see which doesn't work correctly. So that's my approach. And I think this approach is very, very useful for people who want to design their own CPU. So the FPGA implementation, that's on this Bravia kit. We have the lattice semiconductor provided the Diamond IDE, which allows you to synthesize the design from the VHDL or Verilog code, and it has a simulator, it has the programmer, and it even have some debugging tools. So for this PDP1 implementation, I have the top level design is PDP1 chip. And then there are three components, four components. I forgot to add the memory. So PDP1 is the CPU part, UART1, CPIO1, and then the memory module. And the PDP1 LPF, this is the pin-out specification. So here on this board, the FPGA is connected to the LEDs and switches, and then the UART port. Okay, so all these signals come out of the pins, which you can assign almost arbitrarily. But if you assign it wrong, you don't get the signal. Okay, so you have to use the list of I/O pins in the Bravia manual, and assign your signal to the proper pins. And this is all in the LPF file. So if you have all these files, and that you can see here, this GPIO, PDP1, and this is chip, see it, and UART and the memory, and all these 5 files are necessary for the synthesis. And once you get these files in, if you do any edit, if you change anything, and use the file button to say update, and it would compile the whole thing. And it says 0 error and 0 warning. That's good. Okay. So yes, every time if you change anything in a file, it will just go and recompile the whole thing. No, yeah. It just drive. If any file being updated, it will just redo the synthesis. Yes.
warnings as errors?
Yes.
Good.
Yeah.
that's-
But when you started,
Oh, yeah.
yeah,
You'll get a lot of
but
warnings.
yeah, but then you have to worry about the warning.
Oh, yes.
So here, this is the synthesis part, okay, and then the this is the simulation part, okay. So if you are in the tools, you can select the the simulation, and it actually use the another company's simulator. So a couple of months ago, when I was doing this, I would do the synthesis and then do the synthesis to its simulation, generate the simulation files. But it turns out that this simulator from another company just read the same VHDL file and do the simulation all by itself. So it does not require the files be synthesized to the level of simulation. Okay, so you just call it independently. It just read the VHDL file and then run do the synthesis. And this is if I run the synthesis for 10 milliseconds, you can see the UART signal come out. Okay, the clock and all the other signal you really cannot see because they are. This simulator runs on 10 megahertz. If you do 10 milliseconds, it's a couple of thousand instructions or more than many instructions. But you see here, this is the cache return, and this is a cache return. This is line feed, and this is PDP1. Okay, so if you run at 10 milliseconds, you can see all the UARTs outputting the sign on message, and this is the best indication that everything's working or to that point. So that's the simulator. And this is the programmer. Here, if you call out the programmer, it would recognize when you synthesize the process. If you go down to the bottom, and it says JDEC file, and JDEC file is the one JED file. So it will produce the JED file, which is the image that can download into the FPGA and get all the design and the memory and everything down on the chip. And once it's when the download completes, it just boots up. Okay, so yeah, what? yes, you always cross your finger. Okay, so that's the and then if everything's working and then if you have the hyperterminal set up and it will sign up PDP1 cache return line feed and PDP1 version 0.01. So that's the end result. If everything's working, you have it there. Okay, let me just run through the slides, and then I'll do the demo. So the eForth implementation, has the, I'm using F# to compile the eForth for PDP. And then here is in the F#, the scheme of things is that you have a project, and the project is started with a .fex file, okay? And this .fex file initialize several of the Windows interface, and then it loads a bunch of files. And the meta PDP1, this is the meta compiler, and which basically open up a memory, a block memory. You can deposit the PDP11 instructions, and the assembler will recognize the machine instructions and assemble the correct bit patterns into the memory space. And the kernel is the low-level instructions, the virtual fourth engine, and the EF PDP1 is the top level, high level fourth instruction, up to the interpreter, the compiler, the debugger, the memory dump, and the words. So these are the tools in a eForth system. And when you click on the PDP1.fex, it runs through everything and produce a PDP1.memory file. And this file is required by the Diamond IDE to produce a memory VHD file, which would be synthesized into the whole design. Okay, so this is the almost at the beginning of the meta compiler. So it loads in the kernel, and then all the primitives, and then the high level definitions, and it runs on. And after this, when it is compiling, it just spit out the names of the instruction and the address of the instruction. So this is the symbol table that I used to locate the instructions, and then it produce the memory. It dumps the memory to show you the contents. And the PDP11. PDP1 is an octal machine, okay? So the everything shows up clearly in octal. So here, a jump instruction is 60, and then the 42 is the address, okay? So it is kind of you can read the code. If you get used to it. Okay, this is the PDP1.mem file, and this file is required by the Diamond IDE. So you need to specify. You need to tell the memory generator the format, and the depth, and the width, and address radix, data radix. These are the, I think 1 is binary, 2 is decimal, and 3 is hex. And then you have, this is in the address hex format. So you have an address followed by the contents. But this one is, I think the Diamond doesn't accept octal code. It only accepts the binary, decimal, or hex. So I have to present this thing in hex. Okay, this is the fourth virtual machine, and we have the hardware which has two registers, AC and IO. These are the registers. These are the registers programmer is faced with. So you just manipulate data in the accumulator, IO register, and the memory. Okay. But the fourth virtual machine requires many more registers. So the AC is not the capitalized AC is the hardware register, and this lowercase AC is in memory, and this register is always used to store temporarily the content of AC, because AC is used very heavily. Now, almost everything touches AC, so you need to save the content of AC in a safe place, and use the AC to do a lot of other things. And then after it's done, you retrieve the data from the AC register and do what the AC is actually designed to do. Okay, that's IP. IP is instruction pointer. SP is the stack pointer. RP is return stack pointer. Couple S is top of the stack is cached in a separate register or separate memory. And many fourth instructions require an extra location to store things temporarily, and that's a TMP. So here, in the interpreter, the most important is next. The fourth is a list of addresses. Okay. So next is execute at the end of every fourth word, so that it would go to the next word in the list. So here, next is very simple in PDP1. So in PDP1, when we go to one address, you jump to it, the actual function, but the IP remains pointing to this location that you jump from. So the next instruction, you want to get the next instruction, you have to increment IP and then jump indirect through the IP. So this is the once you have the increment and jump to normally, in other more sophisticated machine, you have auto increment function. So when you jump, the IP is already incremented. So that's nice. But this one does not have the auto increment facility. So you just jump, increment it, and then jump. Okay. So this is the most important inner interpreter, and it can be implemented quite nicely here. So here, these virtual machine registers are defined as constants, and the constants are just pointing to the these fixed locations in memory, which are used for these purposes. Okay, now we have the next there, the do list. You want to go, the IP calls one instruction, and this instruction, if it happens to be another list, you have to save this IP address. So ACDAC. So the call, the JSP call in the PDP11, it jumps into the location that's specified in the address field, and it saves the next location in AC. Okay, so the AC, I just deposit into the AC register and decrement the IP, and then load the IP into the AC, and then deposit the IP into the on top of the return stack. Okay, and then get the IP back, put it into IP, and then do the jump indirect. So this way, you nest one level. And exit is a nest. You just load the content of IP. This is where you want to jump back to, and deposit into IP. And meanwhile, you need to increment the IP so that this will pop the return stack, and next do a jump back into the place where you call the last list routine. And do com and do var, these are the inner interpreters for constants and variables. So these can be implemented. So what I want to give you, show you an example is words. So words in the eForth, it is first do the catch return, and the content points to the top of the dictionary, to the last, the name field of the last instruction. So you go from the content, you fetch and see if it is 0. If it is 0, you have searched through the entire dictionary. And if it is not 0, then because that's the name field address. So you have the address, and you can print out the name after space. And the 1 minus the name field in front of the field is the link field. So you have the address of name field, you print out the name, and you back it up by 1, and that's a link field, and fetch it, and you get the next word. Okay, so you just do it repeatedly until the last word or the first word in the dictionary, the link field is at 0, and you have done everything. Yes. The double colon is the meta compiler. Yeah, it's not the fourth. Okay, so this one compile not compiles in the fourth dictionary. It compiles into the virtual memory. Okay, yeah. So that's the. It is almost very similar to fourth, but everything's compiled into the virtual memory. Yes, it's the meta compiler. It is kind of concept which it's the highest level of thinking in Forth. Okay. So here in the memory, this is the word what it appears in memory. There's the link field I didn't show, which is the address pointing to the prior word, and then the 25, 27. This is the first character W with the count 5. Okay. If it is listed in hex, you can see the character and the count, but it is in octal, so it's kind of fuzzy. The first instruction, because it's a high-level instruction, it's a call do list. Okay, it calls do list, and then it saves the IP and point the IP to this next word and start to process this list. Okay, and this is another problem that I have with the indirection bit. So when I have the IP, say the IP is pointing to here, and I jump indirect to the IP, okay, and it actually get to this location, okay, and try to execute 4233 as an instruction. Okay, because it's indirect. It jump to IP point to here, and it would assume that this is an instruction and try to execute it. So because I didn't allow indirection in the memory. So what I did was just put the jump instruction, jump code in front of it, so that it actually jumps to 4233. So this is a way of circumventing the memory indirection, but still get the net effect of indirection. Okay. Hmm? Yeah, it's a problem because when I first put that list there, I want to jump to 4233, but it actually took 4233 as an instruction and tried to execute it, and of course it just failed miserably. Okay, so I have to do something, either activate the memory indirection and put that bit 1 here to indicate that you have to jump. But then if I put a bit here, look at the name field. Name field, many of the half of the words in the name field has that bit set. So you cannot access the name field conveniently. Okay, so I just want to show you the memory content of this word. Okay, this is what if I got PDP1 up and the dump is the one instruction which will take an address and dump 256 words. This is what the memory looked from memory 0. So the first instruction, 604346, it's a jump to 4346. And 4346 is where the code routine is located. So you jump to code and start forth there. Okay, just to demonstrate that it's actually working, I always test these 5 tests, and if all 5 tests works, I say, well, the 4th is done, because interpreters working, compilers working, and then it's the I/O. I have to make sure that I/O works. But in I/O side, I have to do the UART. Have to get the UART work before almost anything else. Okay, if UART doesn't work, force is not going to say anything. Okay, so this, and then the test the I/O, lit up the LED and read the switches. So these are the things that we've done. And the last word. The easiest way to design a CPU is the eForth way, okay? Okay, any questions?
Are you going to be doing the PDP8 any later versions?
Yeah, PDP8, PDP11. VAX. Yeah, I think I need to conserve my brain cells. Yeah, I think the Alzheimer is coming, so. Yeah, hopefully. But the nerve cells only die. Well, they wouldn't regenerate.
Don't make new ones.
Yeah, I've heard that there are something that you can.
Probably in the future, you'll be able to purchase pre-programmed
But do you want?
Yes, yes. Okay, let me go do some demo here. Oh, okay, I can get rid of that. Okay, yes, here I have the yeah, words. Okay, and I just do this hello world to CR quote. Okay, test 2. Oh, sorry. Test CR. Test 2. CR. Okay. I think that's sort of working. I think the more interesting is, of course, the LEDs. Let me see the LEDs. If I do the 0 out, it actually turns everything on. If I say FF out, it turns everything. Oh, sorry, hex. FF out. Okay, and FE out. Okay, and I can read if I do in it's reading all the 18 bits out. The last 2 bits, that's what the output port was set up. So if I do some of the switches, you'll see changes in the other bits. Let me turn all these 4 bits, 4 switches on, and do an in. See, this 4 bits here turned off. Okay, so that's I fixed it yesterday. Couldn't get the I can read the LED, but I couldn't read the switch. And that was kind of told my wife, oh, it's kind of working. I can go do the talk. I don't have to show the switches. Yes.
Can you compare the implementation of PDP1 with the 8080 as far as any kind of metrics, speed or size of memory or how many slices
Yeah, that's a good idea. No, I didn't try. Okay, but the synthesizer has all the information there. So if I let me see, I can let me see. I have the synthesizer there, and I can read the process report. So if I have this report out, I think. Oh, where's my cursor? I don't know. I think that it has all the information there. Okay, but I don't. Right now I don't know how to access them. But yeah, I could do the compare. You know, the EP16 the 16-bit processor is actually the tightest. Okay, I think 8080 is about twice bigger and twice slower. Twice slower. It's the clock speed have to slow down. So, but you know, after that, you know, there's no comparison 8080 with PDP with EP16 because EP16 executes one instruction every cycle, and as you see, the every fourth instruction in 8080 requires about 20, 30 cycles. Okay, and the PDP1 it is better than 8080. But worse than EP16. Yeah, I could get all the matrix out. The speed is not not that's important in the sense that you know this is the clock on the Bravia 2. It is 50 megahertz. So 50 megahertz is, although I've reduced it to 25 megahertz, and it is plenty fast. So to compare, this PDP11 was 200 kilohertz. Okay. Because it takes 5 microseconds for any of the memory read and write. Okay, so the core memory core, the core memory. So it is you know, compared with 200 kilohertz, you know, this is real fast. Any other comments? Yes.
Are you planning on making it available on SourceForge or on the SVFIG website?
I don't know. Yeah, I think the probably I should. Yeah. Mm-hmm. The 8080, I think lots of people has it already, and the PDP. I don't know how much interest is there on this old computer, and I think if I can claim it is completely compatible with the PDP1, it can run all the tape, all the programming on tape. Then
FPGA interface.
yes, yes, have to find a paper tape machine.
ISO punch paper tape format.
Yeah, that's.
Run your paper tape on your hard drive.
Yeah, and yeah, you read the instructions in the PDP1 manual, and it says that it's reading the paper tape 6 holes at a time. So you read 3 lines of holes, and it assembles a 18-bit word, and it just runs from there. Very interesting, but I think. Because you know, I really don't have any experience with PDP1, and don't have any affection, and I think maybe we should go to a computer history museum, and and you know. Yes, read the paper tape there. But I think the only I did the UART the standard way. So if they can make anything the UART way, this thing should work. Okay. All right. Thank you very much. Yeah, it's lunchtime, and okay, we'll see you guys online at 1 o'clock or 1:30. 1 o'clock. Okay. Okay. See you then. Bye-bye.
Station break.